Okay, in the last lecture, we had discussed about the SR flip flop. So, the problem associated with the SR flip flop, that is S is equal to R is equal to 1 is not allowed. So, to avoid this condition, so we discussed about the JK flip flop, how this 1 condition can be allowed in JK flip flop. After that, again in JK flip flop also there is a problem called a race around condition. Okay. So, to avoid this race around condition, we discussed about the master slave flip flop. Okay. So, if I take this master slave flip flop as a block, so the overall inputs of this master slave flip flops are J, K, Q, Q complement, then we have clock. So, if we use this bubble, it is negative edge triggered. Then in addition to this, we have two more signals called preset bar and clear bar. So, we have discussed the operation of this preset bar and clear bar. In order to establish the initial state of the flip flop, we can use the preset and clear inputs. Okay. So, they are called as asynchronous inputs because before application of the clock itself, we can establish some initial state. Okay. So, inside this master slave JK flip flop, so we know that we have one JK flip flop which will act as a master and another SR flip flop which will act as a slave. Now, using this master slave JK flip flop, we can derive two more flip flops. One is called T flip flop. T stands for toggle. So, T flip flop can be obtained by just shorting this J and K terminal together. This is clock. If I connect this J and K terminals together, this is J, this is K. So, that common point you can call as T, Q, Q complement. This is the block diagram of T flip flop. So, we know that the truth table of JK flip flop is J K Q n plus 1. This is actually simplified one, 0 0 Q n itself, 0 1 0 1 0 1 1 1 Q n complement. But what will be the truth table of this T flip flop? This is truth table of JK flip flop. Among these 4 conditions, only 2 conditions are allowed because J and K should be equal. So, only this condition is allowed, this condition is allowed. Okay. So, this condition is correspond to T is equal to 0, this is correspond to T is equal to 1. So, the simplified truth table of this one is T Q n plus 1, T is equal to 0, this is correspond to this. So, simply Q n plus 1 is Q n. T is equal to 1, Q n complement. This is the simplified truth table of T flip flop. T stands for toggle. Okay. Why the name toggle? Is If I fix t is equal to 1, say initial state is 0. So, if I apply one clock signal here, then after the first clock signal this becomes 1, because when t is equal to 1, always the output will be complement of the input, complement of the previous output. So, previous output of 0, now it will be 1. So, after another clock signal 0, after another clock signal 1, and so on. Okay. If you connect this clock to a push button, if you goes on pressing this push button, the output will be changes 0, 1, 0, 1, 0, 1, and so on. So, when does it will changes? If I assume that, say for example, initially q is equal to 0 and this is clock signal. So, this is clock signal, and I am assuming that here I have given a bubble. So, this is negative edge triggered. So, initially before the application of this clock signal, negative edge is this is the first negative edge, this is the second negative edge, this is third negative edge, and so on. I am fixing t is equal to 1 here. If initial state of this q is 0, it will come with 0 from the infinity, this is logic 0. How to establish this initial state before the application of the clock signal? We can use preset and clear signals that we have discussed in the last lecture. Now, at negative edge this 0 will toggles to 1, and this 1 will continue until the next negative edge. At this negative edge this become again 0, again at the next clock negative clock edge this will be 1, and the next negative edge 0, next negative edge 1, and so on. So, this is the waveform at q with respect to this clock signal. So, that is why the name toggle. At every clock signal it will toggles, but because of this negative edge triggered, at negative edge it will toggle. If I design a positive edge triggered, at the positive edge it will trigger, and so on. One important property you can see here is, so if I fix this t is equal to 1 and if I apply some clock signal, then I will get some waveform at the q. So, if I assume that the clock is having a frequency of f hertz, so what is the frequency of q? We can see that this is one period of q, and here we have two periods of clock. Within one period of q you have two periods of the clock. So, the clock period of q is twice that of clock, then the frequency will be half of the clock. This frequency is f by 2. Okay. So, we can use this circuit as a frequency divider also. If I want to divide by a factor of 4, we need two such T flip flops. This is not J, this is T flip flop. You have to design two such T flip flops. Okay. This is about the third flip flop, which is T flip flop. So, mostly this T flip flop will be used in asynchronous counters. So, while discussing about the behavioral modeling, I will discuss the details of this asynchronous counters. Next, another type of a flip flop is called D flip flop. So, in order to obtain the D flip flop from the JK flip flop, we have to connect a NOT gate between J and K inputs. This is J input, this is K input, this is clock, this negative edge clock. So, if I short this J and K, you will get T flip flop. Between J and K, if I connect a NOT gate inverter, you will get D flip flop. This will be D input. This is Q and Q complement. So, D is equal to J is equal to K bar, whereas in previous case T is equal to J is equal to K in case of T flip flop. So, in order to obtain the truth table of D flip flop, if I take the same JK flip flop, simplified truth table 0 0 Qn 0 1 0 1 0 1 1 1 Qn complement. From this you can easily derive the truth table of D flip flop also. So, this is D Qn plus 1. So, D can be 0 or 1. D is 0. So, this D is equal to 0 is correspond to D is equal to 0 implies J is 0, K is equal to 1, this combination. So, what is the output here? 0, and D is equal to 1, D is equal to 1 correspond to J is equal to 1 and K is equal to 0, this one. So, what is the corresponding output? 1. So, we can observe that here this Qn plus 1 is equal to simply D regardless of the previous state, whatever the previous state of this D flip flop. So, if I apply D is equal to 0, output becomes 0, D is equal to 1, output equal to 1. So, simply whatever the information on this D signal will be transferred to the output. Okay. Then the question arises is what is the use of this circuitry then? I can simply connect this D line and Q line. This is D input and this is Q output. If I short this two, so this will transfer the D signal to the Q signal. That is what happening here also. Okay. Then what is the use of this NOT gate, and inside this we have 8 NAND gates. We have discussed the circuit diagram of this master slave flip flop. So, what is the use of this NOT gate and this NAND gate which are present inside this JK flip flop? Because the function is simply you are transferring the D data onto the output. Okay. So, where does this type of flip flop will be useful? So, because this creates the delay. So, if I give D is equal to 0, you definitely will get Q is equal to 0, but after some delay. So, what is the delay? Delay caused by this NOT gate, and inside this we have nearly 8 NAND gates. So, after the delay of 8 NAND gates and 1 NOT gate, you will get Q is equal to 0 here. D is equal to 0, you will get Q is equal to 0, D is equal to 1, Q is equal to 1. So, that is why the name D stands for delay flip flop. Then where do you require this type of delays? Okay. So, this delay flip flop will be used to synchronize two signals with different speeds. So, there is a signal coming here S1, S2. S1 is a faster signal when compared to S2, but finally here I want to synchronize this. Let us assume that here S1 dash, S2 dash. So, I want the speeds of this S1 dash and S2 dash has to arrive simultaneously. So, these two S1 dash and S2 dash has to arrive at the same time. Because S1 is faster, S1 dash will arrive fast if I do not have any circuitry in between this. Okay. So, to synchronize this S1 dash and S2 dash, what is required is S1 is faster, this I will pass through the D flip flop. You can have single D flip flop or you can have series of D flip flops. Then we will connect this directly, so that S1 dash and S2 dash will be synchronized. So, this number of flip flops D flip flop that we have to choose depends upon how fast is this S1 compared with the S2. Okay. So, we can use in the delay equalization circuits. Okay. So, in addition to this, we have some other applications of this D flip flops are, we can use this D flip flop in shift registers. So, in order to construct the shift registers, we need D flip flops. Okay. Even using this shift registers, you can generate the random number generators, which are very much useful in many of the communication circuits. So, I will discuss this shift register also while discussing about the behavioral modeling. Okay. Now, we will discuss how to write the Verilog code for the D flip flop. Okay. So, I will start with a simple SR flip flop, because D flip flop no need of this edge triggered also. Okay. We can have level triggered D flip flops also, we can use in the shift registers. The reason for this one is, so in case of D flip flop, 1-1 condition never occurs. Okay. To get the D flip flops, you can use simple SR flip flop. Okay. So, I will just discuss how a D latch can be obtained. Generally, this latch is nothing but level triggered. Whereas D flip flop, if I write, I will discuss after this D flip flop using SR flip flop, this is called edge triggered. So, I will discuss first a D latch. So, in D latch, because this is level triggered, I will assume this as positive level triggered. So, whenever this we can call as a clock, or simply we can call as enable signal. So, in case of level triggered, normally we will use this clock signal as an enable signal. Normally, this clock concept will be useful for this edge triggered flip flops. So, if I draw the simple circuit diagram of this one, so we know that this SR flip flop is this. This is Q, this is Q complement, then we have S, R, then here we have the clock, but I will call as this clock or enable, I will call simply as enable, EN signal, EN stands for enable. This is a simple clocked SR flip flop or enable SR flip flop, because we are assuming positive level triggered. That means, whenever enable is equal to 1, then the SR flip flop truth table will follows. SR Qn plus 1 is 0 0, Qn 0 1 0, 1 0 1, 1 1 is not allowed. But here if I want to take this D latch, this 1 1 condition will never occur. So, this will be valid only for enable is equal to 1, and if enable is equal to 0, the flip flop remains in the previous state. Now, to obtain the D latch, so we know that between S and R we have, it can be JK or it can be SR. If I connect between these two a NOT gate, and you can call this one as D input. So, D is equal to S is equal to R bar. So, in the earlier slide we have discussed about the derivation of D flip flop or D latch from JK flip flop. Okay. Now, this is actually from D latch. Okay. So, the construction of D flip flop from SR flip flop. So, when D is equal to 0, that implies S is equal to 0, R is equal to 1. So, this is correspond to this. So, what is Q is equal to 0. So, whatever the D is followed to Q. Okay. When D is equal to 1, implies S is equal to 1 and R is equal to 0, implies this is correspond to this. So, output is 1. So, the same input is transferred to the output. Okay. So, in case of D latch, no need of master slave flip flop, when you can use a simple SR flip flop to derive the D flip flop, but this is not the case of T flip flop. T flip flop we cannot derive from this SR in a simple manner by shorting this S and R, because 1 condition is not allowed here. Okay. Now, how to write the Verilog code for this D latch? So, for that I will just simply start with this part, I will call as this is S bar R bar flip flop. Okay. After that I will discuss about the SR flip flop, this is S bar R bar flip flop, this I will call as SR flip flop. Now, I will derive the D latch by instantiating D latch with SR flip flop with S bar R bar flip flop. Okay. So, what is S bar R bar flip flop? Is this portion is S bar R bar flip flop. So, simply I am taking two NAND gates connected back to back. This is Q, this is Q bar, this is S bar, this is R bar. You can verify this also will give the same circuit, this same truth table. So, when S is equal to 0, R is equal to 0, if I consider this combination, S is 0, R is 0 means S bar is equal to 1, R bar is equal to 1. Okay. So, to get this the output of this NAND gate, I should know the other input. Okay. So, if I assume that Q initial is 0, Q bar is equal to 1, this 0 is tied here, this 0 1 becomes 1, 1 1 becomes 0. So, 0 1 becomes 1, 1 1 becomes 0. So, it will get previous state is, if I assume that 0, present state is also 0. Similarly, if I assume that previous state is 1, we will get present state as 1. So, we will get this Qn. Similarly, if I give this S is equal to 1, R is equal to 1, 1 1. So, S bar is 0, R bar is 0. Okay. So, this will give ambiguous state, this is ambiguous state, because both will becomes 1. So, same as the ordinary SR flip flop. Okay. And similarly, if I give S is equal to 0, R is equal to 1, this is S is equal to 0, S bar becomes 1, S is equal to 0, R is equal to 1 implies, So, what will be applied here? S bar is 1, R bar is 0. So, this is 1, this is 0. So, if this is 0, this is 1, because for NAND gate if one input is 0, output is 1. So, this second input is 1. So, this 1 1 will give 0. So, this 0 is tied here again, 0 0 becomes 1. So, output will remains Q. You can easily verify that the same truth table is valid for this S bar R bar flip flop also. Okay. Now, I will take this S bar R bar flip flop as a basic circuit, because this portion is common in D latch also. So, later I am going to discuss about the positive edge triggered flip flop. There also we have this type of the portion. Okay. So, in order to simplify this programming, so we can instantiate these logics. Okay. So, first I will write the Verilog code corresponding to this S bar R bar flip flop. So, I will give the module name I will give as S, I will write all lowercase letters S B R B F F flip flop. This was the notation I am using. S bar stands for this S bar input, R bar R B stands for R bar flip flop. And what are the inputs and outputs of this flip flop? I can give in any order. So, S B I will call as the input. This input S bar, instead of I cannot give this S bar, I am calling this one as S B. R bar I am calling as R B. Q I am calling as lowercase letter, Q bar I am calling as Q B. Okay, this was the notation I am using. So, S B is the input, R B is the input. Corresponding to S B, this S, at this output we have Q, at R we have Q bar. So, I can give in the same order Q, Q B, semicolon. So, this module name I am calling as small S B R B F F. Okay. Later if you want to instantiate, you have to call this name. Okay. So, I will write here the outputs are Q and Q B, Q bar, inputs are S B, S bar, R bar. Then NAND, if I call this NAND gate as G1 gate, if I call this one as G2 gate, NAND is the primitive used for this NAND gate, G1 is the name optional. So, what are the outputs and inputs of this G1 gate? I will give first inputs and then outputs. One input is S B, other input is this Q B, Q B, output is Q. Second NAND gate G2, what are the two inputs? One is R B, another is Q, R B, Q, output is Q B, end module. So, you see the code correspond to this S bar R bar flip flop. So, finally, I want D latch. Okay. So, I will derive this D latch after 2 stages. Then I will discuss about SR flip flop. So, this is Q complement, this was S bar R bar. Now, without clock signal SR flip flop, if I call this one as this, okay, simply you have to use a NOT gate to get SR. As the name implies SR, S bar R bar SR, only difference is NOT gate. So, NOT gate I am going to implement using NAND gate, 2 minimum inputs are required. So, I am going to short this. This is your SR. We can verify the truth table of this one also same as the previous time table, truth table, this truth table. Okay. So, this is S bar R bar, this circuit we have discussed. Okay. Now, what is the Verilog code correspond to this SR flip flop? This you can instantiate, this code you can instantiate. I will call this module as module SR flip flop. The previous module name we have given as SB RB flip flop, because the inputs are S bar R bar. Now, we have S and R inputs. So, I will give the inputs as S and R, outputs as Q and QB, semicolon. Then we require here two voids. So, we have to define two voids and inputs and outputs. Input SR, output QQB, then wire. I will define this as a S bar. So, this is SB, this is equal to RB, SB comma RB. Then we have to instantiate. S bar R bar flip flop. So, how to instantiate? The name that I have given is previous one SBRB flip flop. You can give some name for this one. You can give this name as SR flip flop, comma. What are the outputs and inputs here? Inputs are SBRB, outputs are QQB and module. So, simply we have discussed about the S bar R bar flip flop, which is the basic block. Then simply we have moved on to SR flip flop. Okay. So, by instantiating this, we can easily write the Verilog code. Now, another step is enabled SR flip flop or clocked SR flip flop. So, this clock we are calling as this as a positive level triggered. So, clock you can also call as enable signal here, clock is also enable. Okay. So, if enable is equal to 1, the circuit will be enabled. Okay. So, this of course, you have drawn already the circuit diagram. I will write directly the Verilog code. So, this is the same circuit diagram except for this NOT gate. Here we will be having clock signal or enable signal, then you have S, you have R, the remaining circuitry is same as S bar R bar flip flop. This you call as SB wire, this you call as RB wire, this is Q bar. Now, this part is again common, so I can instantiate this. Okay. Now, what will be Verilog code correspond to SR flip flop with enable signal. You can also have clocked. Say module, you can call this one as SR flip flop clock level. I am giving this as name. Okay. So, what are the inputs and outputs? S are the inputs, corresponding outputs are Q, QB. Then of course, the same as this input SR, output QQB wire SB RB, then you have to instantiate. I am directly writing SB RB FF, this was same name that we have given in the last slide. Then this name I am calling as SR flip flop clock CLK level, you can give any name. So, what are the outputs and inputs of this flip flop? This SB, RB are the inputs, Q and Q bar are the outputs. SB, you can give SB, RB, Q, QB, then end module. So, slowly we started with S bar, R bar flip flop, then we moved to SR flip flop, then we have applied the clock also. Okay. Now, what is D latch? Simply you have to connect a NOT gate between this point to this point. Okay. So, what is the code correspond to D latch or positive level triggered D flip flop? So, I have given the circuit already. This is the circuit diagram. This is circuit diagram of positive level triggered D latch. So, input is 1, outputs are Q, Q bar. Okay. And here also you have to define one wire. I will call this D wire as DD wire. I will write here itself the code, Verilog code. So, module D latch, input is D, outputs are Q, QB. Then we can have input D, output Q, QB. Then we require here SB, RB as the wires, another wire is WW, DD, wire DD, SB, RB. Okay. So, after that, to derive this DD we require a NOT gate, primitive is NOT, the output of this NOT gate is DD, input is D. Then you can call this one as gate G1, this is G1, this is G2, G3. After that we can instantiate that NAND G2. So, what are the output is SB, enable also you have to give input, here you have to write enable. Enable and D, and NAND G3, output is RB, enable and DD. Then you have to instantiate this. So, SB, RB flip flop, and you can give the name of this as some other circuit which is D latch. So, what are the inputs and outputs? Same SB, RB, Q, QB, end module. So, see about the Verilog code correspond to a positive level triggered D latch. Okay. So, we can derive this negative or positive edge triggered D latch also. Okay. using the same basic circuit. So, instead of positive level, and I will discuss about the positive edge. So, you can easily verify that I have explained the edge triggered flip flop using the circuit in the last lecture. So, we can construct now using 3 such latches. This is one S bar, R bar, SR flip flop. This is final output Q bar. This is 2 inputs, and then we have one more this type of S bar, R bar flip flop. Here we are going to apply the clock signal Cp, because this is negative edge triggered. So, we cannot call as enable, okay, we can call as clock signal. So, this is having of course third input also, this is having 2 inputs, the second input of this one is D. So, the D input of D flip flop. Of course, this is connected to this. So, you can easily verify that this circuit will act as a D positive edge triggered flip flop. You can call this one as not latch, flip flop. So, the basic difference between this latch and flip flop is normally edge triggered means we will call as flip flop, level triggered means we will call as latch. Okay. Now, here we have this circuitry, we have code, this circuitry we have code, this we do not have directly code, but we can derive this code of this one by slightly modifying these 2 codes. Okay. So, if I write this Verilog code correspond to this one, module, I will give this name as D flip flop edge triggered. What are the inputs and outputs? We have input is D, Cp, this clock signal, then Q complement, Qb, okay, and then input D comma Cp, output Q comma Qb. Then we require some wires. Okay. So, what are the wires here? You call this one as SB RB wires. Okay. So, what else is required? Here we require some wire. We call this one as some P wire. This is also another wire is required. Of course, this is SB. So, only these 3 wires are required. Wire P, SB, RB. Then you have to instantiate 3 times. Okay. So, I will call this one as flip flop 1, flip flop 2. Of course, this is not exactly same as flip flop 1, flip flop 2. I will call as flip flop 3. Okay. I will discuss how this can be derived from the other 2 flip flops. Then SB RB flip flop, this was the name used. You can call this as flip flop 1, this one. What are the inputs and outputs of this? One is P. How to derive the P? First of all, here we have to write the P. So, NAND RB. So, P nothing but output of this one. So, we will first derive this P. So, flip flap 1, this one. Okay, if you consider this flip flap 1, the inputs are, this is one input, this is input. This input is we are calling as P, this input is Cp. P, Cp, outputs are Q and Q bar. So, of course, one is SB, you can call this one as some S, okay, outputs are S, SB, correspond to this flip flap SB, RB, FF1, we will call this as 1. The code correspond to this one is FF1. So, this is FF2 or FF3. What are the inputs and outputs? We have 3 inputs. Okay. This SB is the one input. Okay. Other input is Cp. The other input is D. The outputs of this one are RB, comma P. Then SB, RB, FF2, FF2. What are the inputs? SB, RB. Outputs are Q, QB. This is end module. So, the code corresponding to this flip flop, I am calling as this is FF1, this is FF, this is FF only, this is also FF only, but this is FF1. So, to derive this FF1 from this 2 input NAND gate, basically here you should have only 2 input NAND gate, but we have 3 input NAND gate. Okay. Suppose if I want to derive a 3 input NAND gate from 2 input NAND gate, this is ABC, I require ABC bar. Using 2 input NAND gate, how to derive? You take 2 input NAND gate, you will get AB bar, you pass through a NOT gate, you will get AB, then you use third input as C NAND gate. So, this output will be now AB is one input, C is the other input, ABC whole bar. Okay. So, using this logic you can write down the code corresponding to this, I am not writing this. Okay. So, this is all about this gate level modeling. Okay. So, in the next lecture we will discuss about the switch level modeling. Okay. Thank you.